Yes. Hi my dear student friends. Now I am going to explain the another traversal technique of graphs, that is depth first search. Depth first search. So this is the second traversal method of a particular graph. So depth first search is a traversal technique. It is also produces the spanning tree as a result. Already I told what is spanning tree, ma? A tree or a graph without loops. A graph without loop is called spanning tree or graph. Here we need to perform breadth first search depth first search. We are using the stack mechanism. Already we know stack mechanism. What is the stack mechanism, ma? So the stack mechanism is nothing but last in first out. What is, ma? Last in first out. LIFO. In short we can call it as LIFO. Last in first out. So what is the best example for it? We can arrange in the CDs. So one by one. First like this, our plates we can arrange one by one. Which one is we are placed first, we can pick at last. Which one is we can place it last, we can pick first, according to this placing order. That is this is the best example for last in first out. So this is the mechanism we are following for stack. So here we need to perform the depth first search. We are using the data structure like a stack. So which mechanism we are following to perform the stack? Last in first out. So with the maximum size of total number of vertices. Maximum size of total number of vertices is nothing but, so how many vertices are there in a particular given graph, that all cumulatively you can call it as a maximum number of vertices in a particular graph to implement the particular depth first search. Select any vertex as a starting point. Already I told in this previous traversal also, if they are not mentioned to start from a particular vertex, so we need to select any vertex from the graph for starting the traversal. So there is no restrictions without mentioning. So for traversal, visit the vertex and push it onto the stack. So which vertex initially we have to select, that will be go and insert into the stack. We need to insert into the stack. So we are using two technical words in the stack for insertion and deletion. What are those, ma? For insertion we are using push operation. For deletion we are using pop operation. For insertion we are using push operation. For deletion we are using pop operation. In the queue, what, ma? In the queue, for insertion we are using NQ. For deletion we are using DQ. Here we are using push operation. So we want to insert an element into the stack, we are using push. So any visited one we need to push into the stack, or any adjacent vertices of particular vertex which is at the top of the stack. So here once we select one vertex, so we doesn't consider both the closed or adjacent vertices. Any one we need to select, either right node or either left node, not both, like in the BFS, breadth first search. So that is the main difference for BFS and DFS. In the BFS we can insert all adjacent unvisited vertices of a particular vertex. In BFS we need to consider only one edge, not all edges of particular node. So that is visit any one of the adjacent vertex of the vertex which is at the top of the stack. That only we can place at the top of the stack. Which is not visit. Suppose that node is not visit and push it onto the stack. Then push it on the stack. When there is no new vertex, if a vertex doesn't contain any new node, So that then we can backtracking. From that node we can backtrack. Means any unvisited nodes are not having to the particular node. That node, from that node we can backtracking. So this depth first search allows backtracking, but breadth first search is not allows the backtracking. So this is the advantage in this particular depth first search, backtracking. So when there is no new vertex to be visit, then we can backtracking and pop one vertex from the stack. Then we can pop that particular vertex from the stack. So these are the steps we need to follow in the to perform the depth first search. So which mechanism we are using? Stack mechanism. What are the terminology we are using for insertion? Push. For deletion? Pop. So what are the maximum size? How many number of vertices are there in a particular graph? That is called as a maximum number of size. Then we can start it from it. Here we need to select any vertex. Is our choice. If they are not mentioned, it is our choice. So here, what is the difference between DFS and BFS? In BFS, we need to consider all adjacent unvisited vertices of a particular vertex. Here, we need to only select one vertex or any one vertex at a time. So, not all closed or all adjacent unvisited vertices. That is the main difference between those. So, here, any vertex is not having any adjacent nodes. Then we can backtrack from the particular node. Then we can delete from the stack. So these are the points we need to follow here. So here I am writing small algorithm from DFS. DFS algorithm. So the first point, push. So here in this previous example, DFS, we are using what ma? NQ. Rather than NQ, here we are using what? Push. Push starting vertex. Push starting vertex and print it. So while second point, while stack is not empty, while stack is not empty, then we can pop. So we can pop is nothing but we can push means we can print. Push nothing but what ma? We can print. Print starting one. Here stack is not empty. So means what? Stack contains some elements. Stack contains some elements. Then we can go for top. Top of the, we can place the P at the top of the stack. Then push means what? Print. Only one or one at a time. So only one or one at a time of adjacent unvisited vertices. If I will mention this, if a vertex doesn't have any adjacent vertices, then make backtracking. Then make backtracking and pop from stack. And pop from stack. Here this point I will put into the bracket. So this is a small algorithm we are going to perform the BFS. The first point, push starting vertex and print it. Push starting vertex. Where we need to push into the queue. So into the stack. Into the stack. So while stack is not empty, for example, you have to take an element. While stack is not empty, here consider this is a stack. Stack is empty or not? Stack is not empty. Here already we are push or print the initial vertex or starting vertex A. So then we can place it as a top of the stack. This is what top of the stack. Then push only one or one at a time adjacent unvisited vertices of particular vertex. So here we can place only one. Then if the vertex doesn't have any adjacent vertices, then make a backtracking from that particular node. Then pop from the stack. This is the algorithm we need to follow. Here I am taking small example for easy understanding. According to these points, here I am taking the binary tree for easy understanding. Here I am using stack. I am using stack to represent. Then result. Result of BFS. So here we need to select any vertex. So if they are not mentioned, we have to select any vertex. Here I am selecting starts from A. I am selecting this vertex A. So what is the first point? Push starting vertex and print it into stack. So starting vertex what A. Push into stack. So we have to push A into stack and print. Print means what? In the results we have to print. So then while stack is not empty. So while stack is not empty. No, it is not empty. Already we are inserting the element here. Then push only one or at a time one adjacent vertices of unvisited vertices of A. So here this is A. Already A is what visited. A is visited. So what are the adjacent vertices of A? B, C. So we are not considered all closed or connected edges of a particular vertex. Only one. You have to remember this point in this DFS. This is a difference between BFS and DFS. In the BFS, we need to consider both BC or CB in either way. So number of ways we need to follow. But here we need to follow only one way. Here I am considered B. Here I am considered B. B is the top of the stack. B is already what visited. B is visited. So then you can go depth like again B. From B we are having what D, E. So we have placed B here. So D, E. So which one we need to select? Here I am selecting this one. We will go deeper and deeper in depth until the dead vertex is reached. Dead vertex is nothing but what suppose we have to consider vertex D. The D doesn't have any adjacent vertices or any adjacent unvisited vertices. Okay, now that is called dead vertex. Okay, now we will go for deep and deeper like this until reach the dead vertex. So that is a depth first search. Depth first search. So then we will consider D here. So then we can place D. We can print D here. So already D is visited. Then now consider D doesn't have any adjacent vertices. Now what we have to do, ma? We have to consider this point. If a vertex doesn't have any adjacent vertices, so then make backtracking and pop from stack. So backtracking means what? We will go from here. Backtracking. So what is the backtracking from D? So then first we can pop from stack. We can pop D from stack. Pop D from stack means we can eliminate D from stack. Then we will make backtracking. So backtracking, what is the next one? Next element in D? In stack B. We will go for B. B is what more? B is already visited. B is already visited. Then we can pop B also. Then we can pop B also. From B, where we have to go? From B, we have to go next element. What is next element? A. A is next element. Here we can observe. In the D, we are having B. We can consider this one. We are having D. But from the D we will go. We are having B. We are having B. B already we what ma? We taken this. From B we are having how many adjacent vertices? 2. What are those? A. This is. Next one what ma? Here also we are having another one. What is this? B. These 2 are the adjacent. A is already visited. So what is unvisited? E. Then we can place this top of the stack. E is the top of the stack. Then come to here E. So E having any adjacent vertices? No. Any unvisited vertices, adjacent vertices doesn't have for E. Then we will go for backtracking. While backtracking, what we have to do? We are eliminating this element from this stack. This stack. Next, then we will go for backtracking. Where we have to backtracking? B. So from B, where we have to go? Already B is visited. Then we can what ma? Pop. Then B can pop from the stack. From B, where we have to go? For A. A. So A having how many adjacent vertices? B, C. B is already visited. No need to consider. So next one what ma? C. Take C is a top of the stack. Take C is a top of the stack. This is already what ma? Now visited. C is already visited. So from C, we can consider anyone, not both, anyone. So I will consider F rather than G. So F is the top of the stack. F is the top of the stack. So now F having any adjacent vertices? No, F doesn't have any adjacent vertices. Now what we have to do? We can delete from this stack. We can delete F from the top of the stack. Now we can make backtracking. Where we have to go backtracking? For C. So F is already visited. F is already visited. Now we can perform the backtracking. Where we have to go ma? C. C is already visited. So C is already visited. Then we can pop C from the top of the stack. Then we can pop C from the top of the stack. But from C, what we are having ma? F and G. F already visited. G is not visited. G is not visited. So we can take G is a top of the stack. You can place this. G is a top of the stack. So then G is already what ma? Visited. G is already visited. So next from G, any adjacent unvisited vertices are there? No adjacent unvisited vertices are there for G. So now what we have to do? We will go for backtracking. Where we need to go for backtracking? C. So next, while making backtracking, what we have to do? We have to pop G from stack. We have to pop G from stack. So next, then we will go for backtracking. So where ma? C. So C is already what ma? Visited. Any unvisited vertices are there? No, all are visited vertices. Then we can pop C from A. We can pop C from A. Then what we have to do? Next, from C we can perform the backtracking. What is ma? A. So what is the last one? A. A is already visited. Any unvisited vertices are there for A? No, all are visited vertices. So there is no unvisited vertices for A. Now what can we do? So we can pop A from the stack. Then what ma? Stack is empty. When stack is empty, automatically it will go and check. Stack is not empty or empty. Then stack is empty. Automatically the controller come out from the loop. The controller come out from the loop. Okay, this is the best example for depth first search algorithm. So now I will explain the another problem. So this is the another example I am taking for DFS. Already this example I am given in BFS also. For the same I will perform. So here I will take a stack. This is a result of DFS. So here we need to, already I told, any vertex we need to select. So I will select the root node, that is vertex 1 here. So what is the first step in algorithm? Push starting vertex and print into the stack. So what is my starting vertex? 1. So push into the stack 1. So in the result also I need to print. So next what ma? This one is what? Visited. This one is visited. So what are the adjacent vertices of this vertex? 2, 3. But here we need to select both. No, we need to select either one. Either left child or right child. Or left edge or right edge. So here I am selecting 2. So then I will push this 2 into stack. So then also I will print here. Next. So where we are ma? 2 is already visited now. So what about 2? 2 have how many adjacent vertices? 2 have 7 and 5 and 1. So 1 is already visited. No need to consider. So 7, 5. In 7, 5 we need to select only 1. So I will consider 7. I will consider 7. Means 7 is visited. So we need to print 7 in top of the stack. Then also I need to print here. So then what ma? For 7. So next one what? 7. From 7, what are the adjacent vertices? 2, 5, 8. So 2 is already visited. No need to consider. The 5, 8. So in the 5, 8, only one we have to select. I will go with 8. I will go with 8. Then I will insert 8 into top of the stack, and also I need to print here. So 8 is also visited. 8 is also visited. So now here, see here, 8. 8 is having any adjacent vertices? Any adjacent unvisited vertices? So no, it's having any unvisited vertices, but it having the only one. This is what ma 8 having only one unvisited vertex, that is 5. Only one vertex, that is 5. So then we can consider or insert, push 5 into top of the stack. Again we have to print here. So then we will go for 5. What are the adjacent vertices of 5? 3, 7, 8. 3, 7, 8. 7, 8 already visited. So which one is 1? 2 is also visited. So 3 is not visited. So I will push 3, and also I need to print here. Next we will go this 3. So 3 means what? What are the adjacent vertices of 3? 1, 5, 4. 1, 5, 4. So 1 is already visited. 1 is already visited. So what are ma? 5, 4. So in the 5, 4, 5 is also visited. 5 is also visited. Already we are print. 1, 2, 7, 8, 5. So 3. 3 now, 3 is also now visited. So now what remaining? 4. 4 is remaining. So we need to push 4 in top of the stack. Next, 4 is also visited. So next, what are the adjacent vertices of 4? Only one it's having. So that is 6. 6 also we have to visited. So that is also print here. So our answer is this. So what are the adjacent vertices of 6? So 4. 4 is also what ma? Visited. 4 is also visited. So there is no other adjacent vertices. 4 is also visited, but here 6 there is no adjacent vertices. So what we have to do? We need to go backtracking. So where we have to go backtracking? From 4. While backtracking, what we have to do? We need to pop 6 from the top of the stack. Then what is the next element? 4. So we will go for 4. So what is the what are the adjacent elements of 4? 3. 6 already popped. 3. So 3 is already what ma? Visited. There is no unvisited vertices of particular 4. So that's why what we have to do? We need to pop 4 from the top of the stack. Where we are right now? 3. So right now what ma? 3. From 4 we will do backtracking. So next what? Here we will this. From 3 where we have to go? For 5. While going to 5, next element what we have to do? We need to pop 3 from the stack. Then next one, backtracking 5. So for 5 there is any unvisited adjacent vertices? 7, 3, 2. All are visited. No unvisited vertices. What we have to do? We need to delete 5 from the top of the stack. Then we will go for next element. What is the next element? We will go for backtracking. We will pay for backtracking. What is the next element? 8. So 8 is already visited. So 8 contain how many adjacent vertices? 7, 5. These are all what ma? Adjacent visited vertices. So then we can pop 8 from the top of the stack. So next what ma? 7. Backtracking. Next what? 7. So 7 is already visited. So what are the adjacent vertices of 7 to 5 and 8? All are visited vertices. No unvisited vertices are there. So that's why we need to pop 7 from the top of the stack. So next what ma? Next element 2. Then we will go 2 from 7 to 2. Backtracking. So next what ma? 2. 2 is already visited. What are the adjacent vertices of 2? 1, 7, 5. All are visited. No one have unvisited vertices or li vertices here. All are visited vertices. So that's why we need to pop 2 from the top of the stack. Next what ma? 1. From 2 where we have to go? 1. From 2 where we have to go? 1. So 1 is what ma? Already visited. 1 already visited. So what are the adjacent vertices of 1, 2, 3? So 2, 3 all visited vertices. There is no unvisited vertices. That's why we need to pop. That's why 2 is already visited and 1 is also visited. So no, that's why we need to pop 1 from the top of the stack. Now stack is empty. Now stack is empty. So in this way we need to perform the depth first search. But depth first search is not only a particular way. We need to perform not only in the particular way. We need to perform in the enormous or n number of ways. We need to perform the depth first search as well as BFS also. So how? Here I am, my starting vertex is 1, but here I will consider the only one adjacent vertex, that is 2. But here rather than 2 I need to consider 1, 3. 1, 3. From 3 I need to consider 5. From 5 I need to consider 8. Like this it will change this scenario. So we will get different types of searching points. We need to traversal by using the depth first search. But while following different types of enormous ways, we need to remember the steps of algorithm, how to perform the BFS as well as how to perform the DFS. So then we can easily perform any type of problem. Yes ma, are you understood all of you? Now I am given one assignment question. All of you have to do it. As for this graph, so we need to, this is an assignment question, all of you. So we need to perform DFS as well as BFS for this. And in this previous lecture, I am given 2 examples. For those 2 examples also, we need to perform DFS. So for this graph, we need to perform depth first search and breadth first search. These are the assignment question for you. I hope all understood. So you have to try for this example. Thank you one and all.